welcome into lecture number 10 of Calculus 3. This lecture is on directional derivatives and the gradient vector. So let's start by doing a little geometric setup for the directional derivatives. You guys will recall, so let's first write this, but let's let f be a function of two variables for the sake of this setup, and assume that it is smooth, or it is differentiable. So let this be a differentiable function. And let's consider the graph of this function as a surface. So we've done this before, right? So I'll draw the surface in red. Maybe we have a surface like this. This is going to be the graph of our function f. And remember how this works. So the height of the graph is determined by z equals f of xy, right, by this function. And the surface sits above points in the xy plane. So let's say we're working at this point right here. We'll call it x0, comma, y0. And up above this point on the surface corresponds the point which we'll call P here, whose coordinates are x0, y0, and then f of x0, y0, which you could call z0 or z0 if you wish. And the idea here is that now we want to take a derivative of this function, of the function f itself, in some direction down here in the domain space. So as we recall, the partial derivatives, right, are defined by kind of slicing parallel to the axes. So the x partial derivative we obtain by slicing parallel to the xz plane, right? So we slice it this way at a fixed value of y equals y0, and then we look at the trace of this curve in the plane, and we draw a tangent line there, right? We do the same thing in the y direction for the y partial derivative. So this one's going to look something like this, right? And then the trace here goes through, maybe it cuts it right there. So the trace of this one, then the tangent line, the slope of the tangent line to this curve that lives in this slice plane, x equals x0, fixed x equals x0, the tangent line to this curve in this slice, that's the partial derivative in the y direction, right? And we did all this in a previous lecture, I think 2 lectures ago. But what I want to do now is ask, what's so special about these two directions, other than that they're the coordinate directions, right? And so we might guess, and we might just assume that it better be true, that we should be able to take the derivative, so in other words, slice this surface in any direction in the domain. So any direction in the domain. And so the way I'm going to draw this is down here in the plane, I'm going to choose a direction vector. So what's got to be true about this direction vector? I'll call this direction vector u, and let's say it has components a and b. And so we want this direction vector to live in the domain. So that's why it only has 2 components here, right? Because it lives in the same space as the domain. The domain of our function has only 2 variables. So the direction vector is, I shouldn't say the vector itself lives in the domain, right? But it lives in the vector space of the same dimension as the domain. So this is in V2 in this case, right? So in V2, our domain of our function is some domain in R2. It's a vector though, and because we only want this to pick out a direction, we're going to require that this vector u is a unit vector. So one of our restrictions here is that the length of u is going to be 1. And the reason for making that restriction, or that condition, putting that condition on our vector u, is that now only the direction of u is going to contribute to our derivative. So once we have this unit vector attached to our point, okay, attached to the point in the domain, we have a direction vector. Then we can imagine slicing our surface the same way that we've done, right, with the other two directions, which happen to be the coordinate directions, but we can slice this way, right? And now we can think about the intersection of this plane determined by this direction vector. So the intersection of this plane with our surface up above, and we can compute the directional, or the slope of the tangent line up here. Right, slope of the tangent line to this orange curve of intersection at the point, P. And so that's going to be called the directional derivative. So that's the geometric setup. The picture gets a little messy once we have all this, but you can imagine down here spinning this orange vector around as long as it remains a unit vector. Right, so as long as this remains a unit vector, then there's a disk around the point in the domain, and you can spin this plane around, and it will, as it moves, it will change the way that it cuts the surface up above. And at every point, in every direction, right, in every direction that it cuts, it could potentially have a different tangent line, a different slope of a tangent line, so a different derivative. All right, well, let's leave this here, but this is the mental image that we should have. And now we want to define this in a way that we can actually compute it. So here's our first definition. Let's, again, let f be a differentiable function. So a differentiable function of two variables in this case. And we'll see how this extends to multiple variables. It's very straightforward. But let's say you have two variables. And similarly, let u, in this case, be a vector in v2, such that the length of u, the magnitude of u, is equal to 1. All right? Then the directional derivative, this is what we're defining here, the directional derivative of f in the direction of u. So in the direction of u, and then we have to say at a point. So this point is in the domain, x naught, y naught. This is given by the following formula. So the notation that we use for the directional derivative is capital D sub u, where u is the direction vector, applied to f at x naught comma y naught. Okay, so there's a lot of notation here, but here's the function, here's the point where we're taking the derivative, and this d sub u, that's the directional derivative. This is going to be defined to be the limit as h approaches 0. It's going to be a difference quotient of, this is going to be here x naught, because we have a fixed point, plus a times h, comma y naught, plus b times h. All right, so there's tiny changes in both the directions determined by our direction vector here. So the a and b come from the direction vector u, and then the rest of the difference quotient is exactly what you expect. F of x naught comma y naught all over h. Okay, and so anytime we define something by a limit, we then have to say, provided this limit exists. But otherwise, this is the definition. All right, so provided this limit exists. So there is the formula, the definition, the limit definition formula for the directional derivative of f at x naught, y naught, or so at the point in the domain in the direction of u. And so the direction u is going to contribute to this. All right, let's take a moment and do an example using this definition. This might be, after we do this once using the limit definition, we'll try to think of a way to do it without having to do that. So in this case, let's say, for this first example, let's say our function is f of xy equals, let's go with a pretty simple function here, but x times y minus x squared, so not too crazy. And then I want my direction vector to be in the direction of, so u is in the direction of this vector I'm going to give you is not a unit vector, so this is going to happen frequently, but let's say 1 minus 1. And then I want to compute the derivative at the point in the domain that's also 1 minus 1. So x naught comma y naught equal to 1 minus 1. Okay, so take a moment and try to work this out. The first thing you're going to have to do is convert, you're going to have to find a unit vector in the direction of v, that's going to be your u, and then you're going to have to plug into this definition and compute the limit. So I'll give you a few minutes, try this one on your own, and then come back and we'll work on it together. All right, let's see how you did. Let's work out all the details here that we need in our formula up here. So first of all, we need to find our vector u, right? So let's start by taking the length of the vector v. The length of the vector v is the square root of 1 squared plus negative 1 squared. So this is root 2. And that means that our unit vector is going to have to be, we want it to be in the same direction as v, but to be a unit vector, so it's going to be v over the length of v, right? And so its components are going to be 1 over root 2 and negative 1 over root 2. And of course, if you wish, this can be written as root 2 over 2 and minus root 2 over 2 if you want. You can use either of these two because those are both unit vectors, so those are fine. And they're the same numbers, honestly. It's just one is rationalized in the denominator and the other is not. Now, we need to compute the rest of this, right? So we need to find f at our point. That's going to be involved. And then we need to find f, the first part of the difference quotient here, f of the point plus ah and plus bh, right? So let's just work it out. So let's just start with f of 1 minus 1. This is going to be 1 times minus 1 minus 1 squared. So this is negative 1 minus 1. That's negative 2. All right, and then we need to also compute f of 1 plus root 2 over 2h, and then negative 1 plus negative root 2 over 2h. All right, that's this b. b is negative root 2 over 2 times h. So what's this going to be? This is going to be 1 plus root 2 over 2h times negative 1 minus root 2 over 2h minus, this one's going to be 1 plus root 2 over 2h quantity squared. And then we notice that this term we can take out the minus, right? And then this is another copy of this. So actually altogether this can be combined to be minus 2, 1 plus root 2 over 2 times h quantity squared. And then we just work this out, right? So this is minus 2 times, as we FOIL this out, this becomes 1 plus root 2h plus, this one's 1 over root 2, so it's 1 square root of 1/2. So when you square that, you get 1/2 h squared. Okay, and you can work this out, but this is exactly what you'll get. And then when we do our subtraction, let's write it out this way. We can multiply through this negative 2. So we'll have negative 2 minus 2 root 2h, and then minus h squared. And now we can put this all in our difference quotient, right? So now our derivative in the direction of u of our function at this point, 1 minus 1, is by definition the limit as h approaches 0 of, we can color code these, right? So it's this is going to be replaced by this. This is just this, right? And that's all we have to do. And then we divide by h. So it's going to be negative 2 minus 2 root 2h minus h squared minus negative 2 all over h, and this is no problem anymore. We've done all the hard work. The minus 2's cancel, h comes out, and this limit is going to be no problem, right? So this is the limit as h approaches 0 of, again, h factors out, we're left with negative 2 root 2 minus h all over h. And of course, in a limit, these h's cancel, and this limit is minus 2 root 2. And so that's the directional derivative of this function at this point in the direction of this vector, which notice we've gone straight for a kind of more complicated version here, but this vector was not a unit vector. So to make sure that this was a directional derivative, we had to first turn this into a unit vector. So that's where this came into play. And then we use that unit vector to compute the limit, right? And so by the limit definition, this derivative is equal to negative 2 root 2. Okay? So I'm sure you're thinking back to Calc 1, where we first made we introduced the idea of a derivative in terms of a limit. We define it by a limit, and then pretty quickly, we do it that way for a little while, but pretty quickly after that, we start finding shortcuts, right? Or not finding, but proving shortcuts. We develop ways to compute the derivatives without having to actually use the limit definition. So the next thing we're going to do is actually do that, right? So we're going to find a way to do this, compute these directional derivatives without actually having to use the limit definition every single time. Now, whenever I teach this section, I remind people, like, you cannot forget about the limit definition because that is the definition, right? This is the definition, and there will be times, maybe there are going to be few in this class, but there will be times when you have to actually go back and remember the definition of the directional derivative to actually compute something or understand it better. But for the sake of this class, here's the next theorem, and this is going to be a good one and a useful one. But this one says, if f is differentiable, and again we're talking about a function of two variables, all right, then the theorem says then f has a directional derivative in every direction. So in every direction. And the key here is that it's given by the following formula. So it's given by this formula. So d sub u of f at x naught, y naught. So this is again for a function of two variables. We'll extend it in a little while. But it's going to be equal to the x derivative of f at this point times a. So we're going to have to write down what a is. But a is the component of the direction vector. Plus the y derivative of f. So I'm using this notation. This is df dx and df dy here. So times b, all right, and so we should write down here where dxf, remember, is just the notation for this. So I'll just write that one, but we know the same is true for y. Just put the y where it goes, right? And this direction vector is where the ab come from, right? So the direction vector is where the components a and b come from. Those are the components of the direction vector. All right, so this right here is our computational formula now, if we can prove that this is indeed true. So it says that the directional derivative is a linear combination of the partial derivatives of the function in the coordinate direction. So df dx and df dy, and then multiplied by the directional components, right? The components of that directional vector, the unit vector. Okay, so let's prove this. We'll maybe not write out in complete sentences every single step here, but we're going to write out a lot of it. So here's what we're going to do. We're going to define a function, g, as a function of h. So we're going to define this g of h to be the function f of x naught plus ah, y naught plus bh. And in this scenario, x naught, y naught, a, b, those are all constants that are given from the problem, right? So in this scenario, x naught, y naught is a point in the domain. Didn't write that. We could write that up here, but I think it's clear from context that x naught, y naught is a point in the domain, and a, b, those are fixed values of the direction vector. So let's define this function, and then let's consider two different ways to take the derivative of this function. So let's consider g prime at 0. Remember, g is a function of h, right? So by definition, this is going to be the following. This is going to be the limit definition is going to be this is going to be the limit. Now h here is playing a different role. This is the independent variable. So let's change this down here to say a u. So the limit is u approaches 0 of, well, I mean, I guess we could still use h here because this is as h approaches 0. Let's use the h because it's going to be more enlightening here. So this, I'm actually going to write this as kind of the other definition of derivative. So g of h minus g of 0 over h minus 0. So this is the limit as x approaches x naught, f of x minus f of x naught over x minus x naught. So the slope, the actual slope version of the derivative. But this is completely correct. And then we write out exactly what this means, right? So this is the limit as h approaches 0 of g of h is this function, right? So f of x naught plus ah, y naught plus bh minus g of 0. Well, when h is 0, g of 0 is just the value f at x naught comma y naught, right? If h is 0, those terms are zeroed out. This is all over h, and then we look at this. Well, this is exactly the definition of our directional derivative, right? So g prime at 0 is equal to our directional derivative here. So this is our directional derivative of f at the point x naught, y naught. Okay, so on one hand, that's the answer. On the other hand, we can try to use the chain rule, right? The chain rule that we learned in the last lecture to compute this derivative of g. So let's write this out. On the other hand, if we put, right, so if we consider g to be equal, so g of h to be equal to f of xy with x equal to x naught plus ah and y equal to y naught plus bh. So these are both functions of h, in other words, x and y. Remember, constant plus constant times h, constant plus constant times h, right? So those are both functions of h. Then we can apply the chain rule, right? So then the chain rule says the following. It says that the derivative of g with respect to h, so dg by dh, is equal to, chain rule, df by dx times dx by dh, right? Plus df by dy times dy by dh. All right? df by dx, df by dy, those are just the partial derivatives of this function f, whatever f is, right? They're the partial derivatives of f. But dx by dh is just a, right? Constant plus constant times h. And dy by dh is just b. So right here, we get, this is df by dx times a plus df by dy times b. And then when we plug in 0 for h, right? So dg by dh at h equals to 0, then these are evaluated at the point when h equals 0. When h equals 0, remember, it evaluates f at x naught comma y naught, right? So this then becomes our partial derivatives. I'll shorthand this now. At x naught y naught times a plus dyf at x naught y naught times b. All right? So what do we have at this point? We have two different notations, but this is still g prime of 0. We've computed g prime of 0 two different ways, right? So on one hand, we have g prime of 0 here. This is another notation, but it still means g prime at h equals 0. And the two answers that we've gotten are the directional derivative on one hand, and on the other hand, we got this linear combination of the partial derivatives, and so therefore they must be equal to each other, right? And so thus we conclude that the derivatives of g at h equals 0, computed two different ways, must be the same, right? So thus we conclude the result here. So duf at x naught y naught is computed by the partial derivative dx df at x naught y naught df dx times a plus dyf at x naught y naught times b. So this is a formula that's going to be easier for us to compute with because we know exactly how to compute these partial derivatives. Okay, so let's work with this now. In the next example, I would like us to use this formula to compute the directional derivative given the following information. So this time, let's let f of xy equal x cubed minus 3xy plus 4y squared. And I want to compute duf at the point 1, 2 in the domain. This function is a polynomial, so its domain definitely contains 1, 2, where we have to know what u is, right? So where u is the direction vector, so I'll say it this way, it's the unit vector that makes an angle of theta equals pi over 6 with the positive x direction. All right, so again, part of the problem here is going to be determining a and b given the information about u, and then from there we can use this formula that we just derived and just proved is the correct formula for the partial or for the directional derivative in terms of the partial derivatives. You can use that to actually compute the directional derivative at this point. So I'll give you guys a few minutes to work on this, and I'll check back in when you're done. All right, let's see how you guys did. So remember, we're going to use this formula here. duf of the point x naught y naught is equal to the partial derivative in the x direction times a plus the partial derivative in the y direction times b, where a and b are the components of the unit vector. So the first step is to find the components of this unit vector, and this unit vector is given to us kind of in trig form, right? So this can be given by the cosine of pi over 6 and the sine of pi over 6, just by using trigonometry. And of course, this then tells us that the cosine of pi over 6, right, is root 3 over 2, and the sine of pi over 6 is 1/2. Okay, so there's our unit vector. Our unit vector u is root 3 over 2, comma 1/2, and now we just have to compute the partial derivatives. So let's do it. We'll do it over here. So dxf, we first have to compute the partial derivative as a function. It's going to be 3x squared minus 3y. And then plug in the point, right? And so then dxf at this point 1, 2 is going to be 3 minus 6, so negative 3. And then similarly, we take the y partial derivative. That one's going to be 0 minus 3x plus 8y. And then again, we plug in the point 1, 2, and we're going to get minus 3 plus 16. So that one's 13. And now we just put all these numbers together, right? So duf at this point 1, 2 is going to be equal to negative 3 times the x component of the direction vector, root 3 over 2, plus 13 times the y component, which is 1/2. And then we can combine this all into a single number, right? So this will end up being 13 minus 3 root 3 all over 2. And that's the best we can do. So there's the value of the directional derivative of this function at the given point in the direction that makes an angle of pi over 6 with the positive x-axis. Okay, so let's talk a little bit now about just the form of this whole thing. So let's take a little bit deeper look at the following situation. So again, let's let f be a function just of 2 variables for now. But let's suppose it's differentiable. And let's suppose we have a unit vector. So let's let our u here, a, b, be a unit vector. So you can call this a direction vector if you want, because every direction vector is going to have unit length. That's going to be part of the definition. And then recall that we have this following definition now. So as a function, we can think of this directional derivative as a function now, as df dx as a function of x and y times a, plus df dy as a function of x and y times b. So a and b are fixed in this scenario, but the directional derivative will change as we change points, right? So look what we can do here, though. The whole point of what I'm trying to say here is that we look at this and we know that u is a vector, right? U is a vector, and its components are now multiplied by these other numbers and added together. So we see we have a sum of, let me highlight it this way, we have a sum of the products of components of vectors potentially, right? So what we can do is we can regard this as a dot product. And look what happens. So regarding this sum as a dot product, then what we end up with is some vector dotted with u, right? And that some vector is built out of the partial derivatives of our original function, right? Then we set this following, we call this the gradient of f. And so this symbol here is like an upside down triangle. This is called the gradient symbol. So gradient of f is going to be the vector whose components are the partial derivatives of the function f. So we set this equal to the gradient vector. And then we can see that our directional derivative, duf, is equal to the gradient of f dotted with this direction vector u in this notation. And if we just write this out just to make sure that this really worked, we have df by dx, comma, df by dy as a formal vector dotted with the direction vector u. The direction vector u's components are a, b, right? And then when we work this out, then yeah, definitely when we get the partial derivative in the x direction times a plus the partial derivative in the y direction times b, and that's exactly what it should be, right? And so essentially what we've done now is come up with a shorthand formula for the right-hand side of this directional derivative in terms of what we're defining to be the gradient vector. So essentially here when I say we set, this is a definition now. We set this to be equal to this. So I'm going to write it out in a few words here, but this is going to be the gradient vector. So we define the following. So the gradient vector. Now, we're going to get into this later in the semester, but this is a formal vector in the sense that the entries of this vector could be functions themselves of x and y, and I kind of alluded to that a minute ago, right? So I'm going to actually call this the gradient vector field. This word field we can kind of ignore for now, but we'll come back to this later in the semester, and then this will all come back and it'll make sense why I'm calling it a field now. But the gradient vector field of this function f, which is here a function of two variables, is given by exactly that formula. But it's good to have this written down formally. So gradient of f, in some sense, is a function of x and y, and it spits out vectors, right? It's going to spit out a vector whose x component is the partial derivative in the x direction of this function f, and whose y component is a partial derivative in the y direction. Okay, so we can extend this very easily to more than two variables. So it extends to more than two variables. I'm going to write straightforwardly. And what do I mean? Well, just in three variables, if f is a function of x, y, and z, what do you think the gradient vector field is going to look like? It's going to be gradient of f now depends on those same three variables, and this will be a vector in three-dimensional space where the components are df dx, df dy, and then the third component is df dz. So however many independent variables the function has, the gradient vector is going to have components in each of those directions. Okay, and so then you could extend this to n-dimensional space, right, in some sense. Yeah, so that's the gradient vector. Now, let's talk about what this gradient vector actually tells us. So what's the geometric intuition behind this, or the geometric consequences of this definition? And so I'm just going to write this as a theorem, and then we will consider the meaning of this theorem and the consequences of this theorem in a minute. But this is a very important theorem. So I'm going to put an exclamation point over here. Very important theorem. So this theorem says the following. Suppose f is a differentiable function. All right, a diffable function of any number of variables. So we'll just, you can in your mind think of two variables, but this could be 3, 4, 5, doesn't matter. But here's what the theorem says. The maximum value of the directional derivative. So the maximum value of the directional derivative, remember this is denoted by d sub u of f at the point x. So I'll write this in vector notation because I want this to be true for any dimension, but use the direction vector. X is just the point in the domain of f thought of as a vector, or written as a vector in this case. But the maximum value of this thing is actually given by the magnitude of the gradient vector at that same point. So this is the value, the maximum value that the directional derivative can have. And not only that, but it occurs, so, or it is attained, we could say, but it occurs when u is in the same direction, the same exact direction as the gradient vector. So the gradient vector at every point is a fixed vector, right? Once you take the partial derivatives, you plug in values for x, y, z, you're going to get a fixed vector here. In this scenario, the vector u is allowed to vary in some sense. So let's draw a picture before we try to write a proof. Let's say we have this point here, P. And actually, let's name it the same way that I did in the theorem, right? So this point here is actually, it can be the point P, but it's represented in this theorem by the vector x, right? It's the point in the domain of the function f. And then we have a couple of things here. We have a couple of more vectors. One of them is u. U is a direction vector, but before I draw u, we do have a gradient vector, right? So we have our function, and maybe the gradient vector at this point is attached here. Maybe it points that direction, right? It could be anything. I'm just kind of making this up. But now the idea is that we want to think of the directional derivative at this point. So of this function at this point, we want to think of the directional derivative, but we don't want to necessarily restrict ourselves to a direction. So let's suppose that this is like a unit disk, or this is the endpoints of all the unit vectors that are attached to this point, right? And so maybe this is one choice for our vector u, and in reality, any vector that starts at x and ends on this circle would be a unit vector, right? A directional vector at this point x. All right, and so what the theorem says is that as this vector u changes, the value of the directional derivative is going to change, of course, right? Because you're changing directions. And what it says is that the directional derivative is going to be maximized when this vector u is pointing in exactly the same direction as the gradient vector. So the gradient vector might not be a unit vector, right? It could be longer or shorter, actually. But it's pointing in the exact same direction as the gradient vector. When it's pointing in the same direction as the gradient vector, then the directional derivative is maximized, and this is its maximum value. All right, so let's look at this and try to prove this. And so to prove this, we are going to want to notice this relationship between the gradient vector and the vector u. And what we can do is these vectors live in the same plane, right, or in the same space. They live in the space determined by the domain of the function. And once we have two vectors, then they always live in a plane, right? And we can let theta represent the angle between these two vectors. All right, so here's our proof of the theorem. It's really straightforward once we understand what we're trying to do here, but let's consider the directional derivative. All right, and this directional derivative is going to be, of course, d sub u of f at x. This is what we're concerned with. Based on our previous discussion, we can write that as the dot product of the gradient of f with u, right? So this is now in some sense a definition. It's the definition of the gradient, right? So it's the gradient of f at x dotted with u. And in this scenario, we are considering x to be fixed. So we're kind of reversing the point of view that we've took in the previous few examples, but consider x is fixed and u is varying. All right, so in this scenario, I mean, it's not going to make a big deal yet, but what's going to happen here? Well, this is a dot product of two vectors, and we have an angle between them, right? So we know that there's a cosine formula for this dot product, and it's then given by the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle that they make, right? And in this scenario, remember that our direction vector u is a direction vector. It's a unit vector, right? And so if this is a unit vector, its magnitude must be 1. And so actually the value of the directional derivative is given by the length, or the magnitude, of the gradient vector times the cosine of the angle that the gradient vector makes with the direction vector. All right? This is, of course, going to be maximized when theta is equal to 0. Right? So this is at its maximum when theta equals 0. So two things happen. Cosine of theta is then equal to 1, and therefore the maximum value over all these direction vectors u of d sub u of f at x is then just equal to this gradient vector times 1, right? The magnitude of the gradient vector times 1, right? And also, if theta is equal to 0, then yeah, then that means that there's no angle between these. So, and thus, u is in the exact same direction, right, as the gradient. Okay, so the gradient vector then has this very, very important geometric meaning, or it gives us geometric information about the behavior of the function, and in some sense the behavior of the graph of the function at every point, right? So the gradient points in the direction that the surface of the graph, right, the graph of the function is changing the most. So we could say then, right, that the gradient, if we wanted to just put this in plain English, the gradient points in the direction of steepest ascent at every point. It points in the direction that is uphill, always uphill, right, where the surface is changing the fastest. So this happens at each point on the graph. All right, so let's do an example in Sage Math and look at we can plot the gradient vector field of a function, the gradient vector field lives in the domain of the function, right? So the gradient vector lives down here with the direction vector and the point. So I'll call this item number 7. I think we're on 7 now. But let's consider the following function. Let's just do a simple one. So f of xy equals x squared minus y squared. This is one of our favorite surfaces, right? This is a hyperbolic. This is a hyperbolic paraboloid. So hyperbolic paraboloid, and remember these look something like this, right? Something like that, right? So there's the surface, and we're going to look at the gradient vector and the level curves plotted simultaneously for the graph of this surface. Okay, now this might be turned a little bit compared to what I've drawn here, but I think it's the right orientation actually. But let's take a look at it. We'll plot this in Sage Math. So I have started off here by kind of pre-typing in some stuff so that you don't have to watch me type. But these are the commands that I'm going to type into Sage Math. And I'm just going to show you, I'm using version 9 of Sage Math. Currently, when I'm making at the time of making this video, 9.2 is available, but I haven't upgraded yet. So there's the version. Now we're going to define the function. So here's the variables x and y. The function is just x squared minus y squared. And I want to make the contour plot now. So the contour plot is, remember, the graph that plots the level curves on the domain space. So on the xy plane, it's going to plot the level curves. It's going to plot 20 of those level curves. So I've set it to plot 20 of those level curves. And let's see, there they are. So these are the level curves of the surface. So remember, if we go back over here, if you were to slice this surface horizontally and look at the heights of the slices and then kind of project them all back onto the domain space, you would see these hyperbolas, right? Hyperbolas at every height. So actually every one of these curves over here comes with its, sister curve on this side. And they come in pairs because it's a hyperbola, right? Same thing here. These curves up here come together with the curve that corresponds down here. All right, so that's the contour plot. Now we want to see how the gradient behaves here, right? So remember that as the height of the surface changes, you're either moving up these curves or down, right? Depending on the way the surface is oriented. So here's how I've defined the gradient. There might be a command, but this is just easy enough to just type myself. So it's the x derivative, comma, the y derivative, right, of the function. So I called it grad f for gradient. And then I want to plot the vector field. Remember, I said that this is called the vector field, right? The gradient of f on the same domain. So let's see how this looks. Now, I named it gf. I want to look at that together with the contour plot. So this is the key here. This is what we really want to see. And so at this point, let me zoom in. We can see that we have level curves, right? Level curves that look like hyperbolas. And so the gradient vectors are getting longer as we get away from the origin. Now let's go back to my sketch over here. At the origin, everything kind of levels off, right? So things are moving in different directions, but they level off. They level off, kind of flatten out at this point here at the origin. But then as you get away from the origin, things get steeper, right? So they're steeper in both directions, just in opposite directions though. And we can see that happening here. So steepest descent, right? The points are moving up toward the origin in this vertical direction. So in the y squared direction, they're moving toward the origin. So this is the portion that actually curves downward, because as the surface is curving downward, then steepest descent is up toward the origin, right? And then the portion that curves upward, that's in the x direction. So I think my picture was turned a little bit, but it matches the orientation of this, so that's good. But these are climbing up, right? The gradient vectors are climbing up away from the origin. And then as you get in between, these things kind of they have this kind of almost like a hyperbolic or parabolic shape themselves, right? Where if you were to follow the gradient and you wanted to take the steepest descent, you would come up here, but you would kind of turn and go up the other portion. So in other words, if you were climbing here and you want to take steepest descent, you'd be climbing toward the origin, but you would turn and then climb up this portion of the surface here, right? And so anyway, The idea here, though, is that every one of these vectors represents the gradient, and those gradient vectors are pointing in the direction of steepest descent. And one thing that we can notice is that these vectors, they're not attached at the exact same points as the level curves, but the ones that are, you can see they look like they're perpendicular to the level curves, and it turns out that they always are. And it's going to be an exercise for you guys to actually prove that the gradient vectors are orthogonal to the level curves of the surface in the domain, right? The level curves live in the domain and the gradient vectors live in the domain. And then together these things come to, they behave in this way at the same time, right? So they're orthogonal to one another. So the gradient vectors are orthogonal to the level curves. All right, let's look at one more thing now that we've taken a look at our Sage math just to get a picture of what that looks like. We'll call this item number 8. Not only are the gradient vectors orthogonal to the level curves, but they're related to the tangent planes, which should not be a surprise. But let's think about this. So let's recall that for a function of two variables, so if f is a function of two variables, so if f is equal to f of xy, then the tangent plane to the surface, so to the graph of f at a point, so at f of x naught, y naught, right? This is given by the following formula. And by the way, the book frequently does this, so we can do it too. We'll call this z naught equals f of x naught, y naught. Then what is it equal to? Well, z equals z naught plus the partial derivative in the x direction at this point times x minus x naught plus the partial derivative in the y direction at this point, x naught, y naught times y minus y naught. And then if we rearrange this a little bit, then this can be written as df by dx at the point. This will be a number, right? This will be a number times x minus x naught plus df by dy at x naught, y naught times y minus y naught, and then minus z minus z naught equals 0. All right, and now this is in the form, if we kind of underline these, this is in the form a x minus x naught, b is y minus y naught, z or c times z minus z naught, right? And remember that these a, b, c, these form the normal vector. So these form the normal vector to the tangent plane if we think back to calculus 2 and normal vectors of planes, right? So this is the normal vector to the plane. So to the tangent plane. So it's not exactly the gradient vector, right? But it's very similar to the gradient vector. It's like the gradient vector and then a minus 1 in the z coordinate, right? So it's like an extension of the gradient vector. So what we have then is that our normal vector to the tangent plane is df by dx, df by dy, and then negative 1. So there's a normal vector to the plane. So let's use this information to find a formula. And you don't even necessarily need to put it in vector form, but let's just use the gradient though to find a formula for the tangent plane to the surface, so to the graph of f of xy equals 4y square roots of x at the point 4, 1. All right, so that's what I would like you guys to do. This will be the last thing we do in this lecture, so give this a shot, and then when you come back, we'll finish off the lecture. All right, let's see how you guys did. The first thing that we can do here is compute the gradient vector. So let's do it in 2 steps. And again, this isn't the only way to do this, but because we're talking about gradient, I want to compute the actual gradient of the function, and then we'll plug in, find the gradient vector, and use it to write the equation of the tangent line. So the first thing we need to do then is take these derivatives, right? So the x partial derivative here, remember for the x partial derivative, we treat the y's like constants. So it's going to be 4y over 2 square roots of x, and that'll reduce, of course. And then the y partial derivative is just 4 square roots of x, right? And so this reduces to 2y over the square root of x, comma, 4 square roots of x. And at our point, the gradient, when x is 4 and y is 1, we end up with 2 times 1 over 2 in the first component, and then 4 times 2 in the second component, and this is, of course, 1 comma 8. Right? So there's the gradient vector of this function at this point. This is the vector that points in the direction where the surface is changing the most, right? The steepest ascent, we called it. Now, to find the formula for the tangent plane, we also need to know the value of the function itself. We could have done this first, right? But the value of the function itself at this point. And so this is going to be 8 as well, right? 4 times 1 times 2, that's 8. And now we just put it all together. So z is equal to 8 plus, and then we use these as our slopes. 1 times x minus 4 plus 8 times y minus 1, right? Y minus 1. Okay, and this is it. I mean, we could work this out more, but that's good enough. So that's the equation of the tangent plane to this surface at this point, 4, 1. All right, I'm going to leave this lecture here and talk to you guys in the next one.